Great. Yeah, thanks a lot. And thank you everyone for being here. Going to go ahead and drop the slides right now so you don't have to wait to see them in the chat. And let's go ahead and get started. I'm going to be talking about Paved2Paradise today, which is a pipeline for generating synthetic LiDAR data cheaply and with diverse samples using natural data. And so for some context here, I am a machine learning engineer at John Deere, and I work on the project being showcased here. This is an autonomous tractor that operates in orchard environments. And this is a clip from a video I was shown at CES this year. And as you can see, this tractor is pulling this implement, driving through these orchards. It's a pretty complex environment. Lots of trees, obviously, lots of places for people to be hiding, lots of weird shadows, things like that. So that's just a little eye candy for the setup here. And so the motivation for the task I'm going to be focusing on today is human detection in orchards. And so the challenge, as it is with all of these machine learning projects, is that things are very varied. In this case, both the orchard environments and people are highly varied, right? And so these orchards have, each tree is different. Each tree can be slightly different in terms of its spacing. It can be older, it can be younger, all these different factors. And of course, as most people here know, deep learning models need to see as much variety as possible during training to improve their performance in their wild. So if we want the models to be able to generalize and work in all different types of orchard environments, we need to expose them to as much data as possible. And so the main challenge here, though, is getting all of that data. Things like ChatGPT, they have a huge amount of data on the internet just available to them from the start, right? In our case, we're not so privileged. And so we need to think about how we can get a bunch of data of humans in orchards, right? And so if you were just to proactively go out and try and collect data that will represent all of the variation that you'll see in the wild, there are several sort of factors here that I think are separate that you need to be considering. And specifically, if we consider all those factors together, basically the diversity of possible samples grows combinatorially. And so specifically, we can have different backgrounds, where a background, I mean, is a single snapshot of a specific location in an orchard. And so you can see in a single orchard, you can have many thousands of different backgrounds, where we're talking again about different trees, potentially, or different ages of trees, different spacing of lanes, things along those lines. Different times of the year. So trees, have leaves and sometimes they don't have leaves, things like that. We have different types of objects. And so humans are a particularly tricky kind of object in that they are non-rigid. And so that means that they are bendy and stuff. And so you can't just rotate them to get a sense of the entire object. They bend. And then obviously humans are a wide variety of shapes and sizes as well. And then, so yeah, the humans are, the different shapes and sizes would correspond to the different objects. And then P is the poses. And so again, like I said, humans are non-rigid. And so there's all these different ways that the human can be configured. And then lastly, there are the locations where the human can actually be placed in the scene. And so for any given background, there's a number of different places where the object could be placed in that background, where each one will look different from the LiDAR's perspective. And so just as, a little example here, if you take these numbers for each of these factors, you get 10 billion different possibilities, which is obviously going to be impossible to collect if you try and send people out and try and collect all of that data. So the question is there an effective alternative? And so, yeah, for the orchard environment situation I'm talking about here, the reason it's so you can't just passively collect all this data is because humans are kind of rare in orchards in these setups. And so the idea around Paved2Paradise is to exploit the fact that point clouds contain information about the 3D geometry of the scene. So can we sort of partition our collections to allow us to get that combinatorial diversity? And so basically, the strategy here is to have two different collection paths. One is to collect LiDAR data of people performing poses in a parking lot or just any kind of flat, empty area where it's easy to isolate the human in the scene. And then combine that with a LiDAR data of captured by driving around an orchard without any humans present. And so because this part can be just passively collected as the tractor is operating, you basically get a ton of background data just for free without doing any extra work. And so that basically drastically reduces our complexity of the amount of time we got to spend collecting data. And basically, when you do this parking lot setup, you are able to, as I'll talk about a little bit later, but basically you can eliminate the location factor. And so this greatly simplifies the amount of data that you need to collect to be able to generate a really diverse set of samples for training. Okay, and so this is kind of the pipeline as it existed for the papers. There's been a little bit of modification since then, but I'll talk more about those a little bit later and do a little demo. And so basically, again, we're going to collect our object. There's a leveling step to make sure the point clouds are aligned between the background and the object scenes. We're going to extract the human or object. We're going to place them in a new location, and then we're going to combine them together to create a final scene where that combination step is going to involve some occlusion and simulation. And so walking through the steps here. So the first step, again, is to record people performing different poses in a parking lot. And so the nice thing about this is if you record the human very close to the LiDAR, their point density, there's going to be a lot of points. Their density is going to be very high. And that's going to basically allow us to do the LiDAR simulation effectively later. So essentially what this step is doing is it's removing that location factor, the L, from that combinatorial explosion piece. And we're going to basically be able to simulate all of the rest of the L's by collecting the object from a very constrained location. And essentially what that means you can do is by only collecting data for a few minutes for each individual, you have enough data to generate many different diverse scenes. And so basically you can scale this part up very quickly. You can get through many different people in a short amount of time and have a really create a really large data set of object or human assets in this case. So the second step, like I mentioned, is the easy part, in that if you just have some whatever vehicle you're working with, or whatever robot you're working with, operating on under normal conditions where the rare object is not present, you basically just have to collect data. And assuming you haven't fully automated things at this point, and you have a human operator, you can just make sure the human checks whether or not a human's present. And as long as they verify that there aren't any human present in the scenes, you can just use all of that data and put it into a database of your background scenes. And so the next step is to draw bounding boxes around people. And so this is probably maybe the biggest initial bottleneck, and maybe is not even necessary depending on your task. If you don't actually need bounding boxes, you can obviously automate the extraction of the human point cloud if you use a simple environment, right? Basically, all you got to do is find points that are above the ground, and you can extract those out if you limit your point cloud region to the performance area, if you will. And so once you get some labels, though, you can kind of quickly scale up the rest of the bounding box annotation by training a model on that limited data set. And so the reason that this works is because, like I said, you can automate the extraction of the human points, right? And once you have just the human points, it's a fairly constrained machine learning problem. And so with just a fairly small number of bounding boxes representing different sort of configurations, you can get a pretty accurate model to give you pre-labels essentially, or machine generated labels. So in this case, I was using a PointNet++ to generate those automated labels. But again, there's different approaches, and you might not even need this if you're not using cuboids. So the next step is to put the people in orchards. but it's perhaps not so straightforward, particularly because we're interested, like I said before, in augmenting the data by moving the person to a specific location in the scene. And so what you see here is a sort of naive cut and paste approach, where the human from the parking lot scene was cut out and then is simply pasted into this orchard scene. You can see that even though the human hasn't been moved at all in terms of the XY coordinates, they're below the ground. And so we need to sort of be careful about how we're moving the human in the scene. And so that's where this leveling step comes in. And so this is a really sort of simple algorithm, but works really well in practice, at least for these orchard scenes and also urban scenes, as I'll talk a little bit about later. But basically, the step is to lay out, the steps are to lay out a grid of points below the scene. Usually centered, you can center it at the LiDAR, or you can center it at where the human is going to be placed. I think centering it where the human is placed tends to work better. You find the nearest neighbors for all those grid points from the points of the scene, and you basically classify those as your ground points. And then using those ground points, you can just estimate a ground plane, and you can rotate the scene and level it so that it's, or you can rotate the scene so that's now level. And so you can compare this one to this one. After we do that rotation and leveling, we can see that the human looks very natural and placed on the ground. And so we're off to a good start there. So another piece to pay attention to is the perspective of the LiDAR in the scene. And so what I'm showing here is kind of how this perspective plays out. And so if the coordinate frame here is your LiDAR, and it's looking at this cone with the cone oriented in this direction, the LiDAR is only going to see the bottom of the base of the cone, right? And so this is the point cloud it's going to see. If we were to, in 3D space, physically move the cone to the left of the LiDAR, this is the point cloud we would see. So we'd be seeing like the side of the cone. But notice that if we were to take the point cloud from the first configuration and move it to the left of the LiDAR, we would get a physically inaccurate point cloud for the scene. So not only are we not seeing the side of the cone, but also this circle of points isn't what a circle would look like to the side of the LiDAR. When the circle gets moved to the side of the LiDAR, you'd only see the front edge, basically, or the edge that's closest to the LiDAR. And so, in a sense, moving this point cloud around in space without considering perspective gives you a point cloud that's wrong in sort of multiple aspects. And so the trick here is to use this perspective consistent placement. And so whenever we find a different, when we sample our object and then sample a place in the background to place the object, we enforce this perspective consistency by only allowing rotation around the axis of the LiDAR, the vertical axis, and then moving the object basically forward and backward, perpendicularly to the LiDAR. So just straight back and forward. And that gives us this perspective consistency. So you can see here, we took this cone, we wanted to move it over here, which is a little bit closer and over here. And so all we did was rotate it over here, and then we moved it a little bit closer or further back along that direction. And so we basically have a nice set of points now in our final scene, but we're still not quite done. And the reason is the person would be occluded by the tree, in this case, in a natural scene, and they would also have fewer points when they're further away. And so with a LiDAR, right, it's shooting out beams, as it, some rotate and some are static, but basically they all shoot out a bunch of beams that will bounce off objects and come back, right? And so because those beams are spreading, when an object is closer, it will be hit by more beams, and when it's further away, it'll be hit by fewer, and the pattern of the points on the object will be different. And so that is what this next step needs to consider. We need to figure out how to occlude and simulate those final points. And so the basic idea is that if any of the orchard points are close to the ray corresponding to a human point, we should be dropping that human point. And then otherwise, we will be interpolating real points on the human to find the simulated points. And so this is the basic setup here for these two steps. And so these figures come from the paper, which is linked to in the slides, but goes into more sort of mathematical detail. But anyway, they're basically the inverses of each other. We're shooting out a beam, and so the B's in this case are the background points, and over here the O's are the object points. So we're shooting out a beam, and we're using some geometry to find the closest points. You can see that this says it's the old. I'll talk a little bit about why this approach is maybe not optimal in a second. But anyway, you shoot out the beams, you find the points, and you either occlude or you interpolate between the closest points to the beam that project onto the beam, and you use that as your simulated object point. And so, like I said, there's some issues with this old approach. And so when I was originally developing this pipeline, I was focused on the point pillars model. But if you use that occlusion, that sort of distance-based occlusion step, you end up getting artifacts in a range image, the range image representation of the scene. And so if you want to use range image models, these artifacts can make it kind of tricky to deal with this kind of data. And so the question is how to fix that. And the solution is actually the obvious one that I probably should have did in the first place, which is to just paste the simulated points into the scene. And so what you can see here is we have our background scene, and then we have the simulated points that are generated by moving the object to a new location, sending out the beams and seeing where it strikes the human. And then to combine them now, we just simply move these points into the combined scene and just take the closer of the 2 points for every range image point. And so if you're not familiar with range images, they are basically like they're set up like an image. And so there's a height and width array, and each pixel corresponds to a different beam where for the azimuth, so the angle as the LiDAR beams are spinning around, and then the elevation, which is the angle, going up and down like that. And so there's 2 coordinates basically that index every single beam from a full revolution. And so with that, we know each coordinate for each of these simulated points and each coordinate for all of the background points. And so we can then just combine them by taking the closer of the 2 points for every single point from those 2 scenes. And that gives us this new image, as you can see here. And it looks much more natural, and there's none of these weird artifacts that I showed before. One kind of interesting trick is that, or it's not really a trick, it's just a necessary step really. When you're doing this point cloud simulation, the number of beams, right, is very large. And so if you were to just do that projection to find the points for interpolating on all of the beams at once, with the original object points, you run out of memory very quickly, essentially. And so the trick here is to basically divide up the scene into these cylindrical slices, and then only do the beam simulation for each of those slices. And of course, if the object is far away, you can only focus on one particular cylindrical slice, for example, and that will that allows things to that reduces the memory footprint by a lot. It makes it manageable to do. So after all these steps are combined, we get a result like this, where we have the human that was collected in a completely different context in a parking lot scene has now been entered into this new scene and put in a completely different location. And we have realistic occlusion and simulation to give us a really realistic looking final scene that we can use to train our models. And again, we have now taken this sort of combinatorial explosion of possible data, and we've reduced it to a much smaller amount of samples that we need to actually collect, but we can still generate this diversity by sort of combining these pieces in a clever way. And so to give a proof of concept, sort of, this is also discussed in the paper, we collected 21,000 human frames collected from 48 individuals. And this was done, this was basically our first attempt at doing this. And we did this in one day with basically one intern. And so this kind of gives you a sense of the scale that you could potentially do here. All you need is, this was just with one LiDAR, you can just basically shuffle people through really quickly by having them show up, do some like weird poses, do some walking around, stuff like that, and then next person out. And then with the orchard frames, we did just one collection and had these 6,700 orchard background frames. From that, we generated 500,000 synthetic samples. We did some training time augmentations here. Specifically, the more interesting one potentially is this bumping, where we basically rotated the scene a little bit based on the rotations we actually observed through all of the data. And then finally trained point pillars model, which is kind of like classic architecture for doing 3D object detection, but is actually still basically the basic outline here is still used in a lot of state-of-the-art 3D detection tasks for LiDAR. And so here's the outcome. And so again, this model was trained exclusively on synthetically generated data from these separated data collection setups. And we went out and did a second collection where we had in a different location and had a couple of people sort of walking around in the scene to test the model's performance. And so you can see as soon as the humans show up in the scene, the model starts detecting them. Have them doing weird poses like that, like reaching up at the tree. Notably, this model was only trained on samples with a single human in each sample as well, which is kind of interesting because it generalized to detecting two people at once. So you can see that we're consistently detecting the humans no matter where they are on the scene. So as the human got really close there to the LiDAR, they were heavily cropped because of the field of view of the LiDAR, but we were still able to detect it because we're able to simulate those physical effects with the pipeline. So now we got a heavily occluded human over here behind some branches. The model still has no trouble detecting them. Again, occluded now. And we have some weird bumps that you just saw, but because bumps are natural and show up in as we're collecting background data, we were able to handle it. The model was able to handle it effortlessly. And so this is kind of a testament to the potential there. Oops. I did a second experiment with the KITTI data. Basically, the main takeaway here is that using humans that were collected with a completely different LiDAR setup than what's in the KITTI data, but just inserting those humans into those scenes, but simulating the LiDAR that was actually used with the KITTI data, a model trained on that is actually able to work really well in terms of detecting pedestrians in that data set. And so, yeah, I'm excited to announce today that that fix I mentioned with the pasting, and additionally, I've added color support for Paved2Paradise, and so this is available today, right now, in the GitHub repo. But basically, this point interpolation step I mentioned here, it actually immediately works with colored point clouds. And so basically, if you might have noticed on the tractor that there are both cameras and LiDAR. And so if you have a way to color your point clouds, you can immediately use this same pipeline to generate synthetic color point cloud data of with the humans being moved around and stuff like that. And so, yeah, the reason it works is because we're just doing this interpolation, basically. We still find the two closest points when we're doing a simulation, and then we just interpolate between those with the colors rather than the actual point coordinates to get the final point color, and that gives us our final scene. And so, yeah, there's a paper, like I said before. In addition, there's a public repo. And now I'm going to do a quick demo just to show give you a sense of how the GUI works. And so, like I said, this is all in the repo already. If you clone the repo, all you have to do is a small pip install, some requirements, and you'll just running this Python Paved2Paradise, you'll start up with exactly what you're seeing here. And so this gives you a sense of how the app works. And so we have our object point cloud over here. The background point cloud is in the middle. And we have this new location that we're moving the object to. And so what you can do is kind of click around to move the object anywhere you want. And just as a quick proof or demonstration of why color matters, if we put the person, like kind of right in front of that trunk, this is what it looks like when there's no color. And so it kind of looks just like a thick tree trunk. But if you, of course, add color, it becomes a little more obvious that that's a person enclosed. So yeah, this app has all of these sort of geometry and LiDAR configuration pieces available to you so that you can play around with different sort of setups. For example, you can see how the object grid and ground plane are being generated. You can also show the beams for the LiDAR. And so this is a good check for whether or not your particular LiDAR setup is correct. And so we can see that the beams are coming out and striking the person as we are expecting. Also, another check is these LiDAR cones, where you can, again, verify that the geometry of your scene makes sense. And so we can see that the LiDAR, the points that aren't visible in the background scene make sense based on the geometry of our LiDAR. And then you can also, see the effects of occlusion. So we can see that the background is there now, and just clicking in and out, seeing what that happens. And then you can also show the range images, which gives you a sense for how the scene is being constructed with that occluded with that new cut and paste sort of range approach. And so we have our background range image here, the simulated points after being occluded, and then the final scene as constructed up there. And so, yeah, I think I'll stop there. I'm happy to take any questions people have them. Thank you.